Okay, now that we've done the simulation, let's get into the question. L1 and L2 are two light bulbs and have the following ratings. L1 is 36 watts with a voltage of 20, and L2 has 48 watts with a voltage of 32. The two bulbs are connected as shown in the circuit diagram. The battery has internal resistance of 0.6 ohms. While conducting, wires and the ammeters have negligible resistance. R1 and R2 are resistors. So if we analyze the circuit before we even get into the question, we know that L1 and L2, so that means L1 and L2 are in parallel. So basically R1 and L1 are in parallel with L2. So this voltage, so these two are in parallel with L2. So that means the voltage across both of them will be equal. As we saw in a parallel circuit, the voltage is the same. So the voltage is the same. And what we can also be sure is that the current here at A1 will be the total current, because that will be the current before it splits here in this section, because it will split in this section, but A1 will be a reading of the current before it splits in that section. After splitting, it will come back together here. So that means the current flowing through R2, the current flowing out of R2 will also be the total current. But the current flowing through here won't be the total current, it will be the current that is split. Even the current flowing through A2, we know that it will be the current that is split, so it won't be the total current. But we know that the current flowing through here and the current flowing through here, when you add them together, they will give us the total current. So without further ado, let's get into it. So define the term power. So power is the rate at which work is done, or work done per unit time. That is power, the rate at which work is done, or work done per unit time. So calculate the reading on if both bulbs operated as rated, calculate the reading on ammeter 2. Okay, so L2, what do we know about L2? We know that it has a power of 48 watts and a voltage of 32. So that means to calculate the ammeter, the reading on the ammeter, which means the current, we can use the formula for power, which is power is equals to VI. Because we have power, we have power, and we have what? Voltage. So we can find I. So I will be P over V, which is 48 divided by 32, and then I will give us 1,5 amperes. So then we can remove this, and then we know that, then we'll know now that here we have 1,5 amperes current flowing through here, through A2. And the second question says reading on ammeter 1. So the reading on ammeter 1, we know that the reading on ammeter 1 will have to be, so the reading on ammeter 1 will be the total current. Why? Because as you said, it will be the current before it splits. So the current will split into these two sections, and then it will combine back here, and then it will flow as one again. So that means the current flowing out of R2 or flowing into R2, because the current flowing into R2 will be the same current flowing out of R2. So the current at R2 will also be the total current. So that is why we say L1 and R1 are in parallel with L2, but L2, L1 and R1, all three of them are in series with R2. Why? Because R1, if I combine the current flowing through L2 and R1 and L1, I get the total current, which is exactly the current that is flowing through the resistance 2. So that is why I say the resistance here at 2 carries the total current. So that is why the resistance at 2 is in series with L2, L1 and R1. Okay, so the reading on ammeter 1, so we can use the same formula again. P is equals to VI. I mean, there are a lot of power formulas, so we can use any of them. I'm just using this one because it has what we need. We have power, we have voltage, we just need I. So I is equals to P over V, which is, for L1 is what? 36 divided by 20, which is 1,8 amperes. So then we can remove this. So now we know that the total current flowing through L1 is what? The current flowing through L1 is what? 1,8 amperes, which is the same current also flowing through R1 because they're in series. And we know that in series, if in series, they share the same current. So that means, so this is the current when it's split. When it is split, we have 1,8 this side and we have 1,5 this side. So that means when we add these two together, we should be able to get the total current. So I total will be I, so we'll say call this I2, we'll call this I1, will be I1 plus I2, which is 1,8 plus 1,5. And that will give us a value of 3,3 amperes. Okay, now we know the total voltage flowing, so we know that the total voltage coming out of here is I is equals to 3,3 amperes, which is the same to current here, which is I is equals to 3,3 amperes. Now, as we've said, we've mentioned that we know that which comes down to the 8.2.3 says calculate the resistance of R1. We've mentioned that this are in parallel. So this is in parallel with L2 is in parallel with R1 and L1, which means they share the same voltage. So that means if we look at the voltage of L2 is what? Is 32. And if we look at the voltage of L1 is 20. So we might ask, but why is it different? Because we said they should have the same voltage if they are in parallel. They are still the same. The only reason why L1 has a voltage of 20 volts is because it's in series with R1, which means R1 took the rest of the voltage. So that means the other 12 volts is lost here at R1. Because we remember, because R1 and L1 are in series, that means they will share the voltage. But both of them, when I combine both of them, when I add them together, they give me 32 volts. That is why I said R1 and L1 are both in parallel with L2. So then from this we can deduce that, oh, therefore R1 should have a voltage of 12 volts. So we can add that officially and say voltage of R1 is equals to the voltage of L1, no, not L1, voltage of L2 minus voltage of L1, which is 32 minus 20, which is the 12 volts that we just talked about. Now after we've calculated 12 volts, now we can calculate the resistance of R, because remember the first Ohm's law says I is equals to V over R. Now what do we need? What are we looking for? We're looking for the resistance. Do we have the voltage? Yes, the 12 volts. Do we have the I? Yes, we just calculated it in the previous question, which is 1,8, because the same current that flows through L1 is the same current that flows through R1. So therefore, that means the resistance is equals to V over I, which is the voltage is 12, and then I is 1,8. So that means R is equals to 6,67 ohms. 6,67 ohms. Okay, then we can remove all this. Okay, here's 1.8 amperes, 20 volts, 12 volts, and then we just now calculated 6.67 amperes. Okay, now they ask us to calculate the EMF of the battery. Oh, EMF, remember what you said. So EMF is the total power supplied by the battery. So the total power supplied by the battery is the EMF, but the one distributed across the circuit, it's not the total EMF. Because why? Because some of the voltage is lost due to the internal resistance of the circuit, which we saw in that simulation. That simulation was supplying a total of 34 volts, but we saw that across the circuit sometimes it was 29, sometimes it was 32. So that's what we talk about when we say that internal resistance, some of the voltage is lost due to internal resistance. So what's the formula for EMF? EMF is equals to total total, which is the total current, multiplied by R plus internal resistance. So what do we need? We need the total current, which we already have. What do we need? We need internal resistance, which was already been given. We said it. They said it's 0.6. Now we need the total resistance. The question is, do we have the total resistance? No, we don't have the total resistance, which is what we need to calculate. Okay, so let's take it step by step. Okay, so we need the resistance of, okay, so let's start with the top part. This top part, that means we'll need the resistance of L2. We don't have its resistance, we have the voltage, which we were given as 32. We have the current, it's easy to calculate the resistance. So therefore, what is this? R is equals to V over I. So the voltage is 32 and the I is 1,5. So the resistance is equals to, which gives us the value of 21,33, and this is resistance, so it's ohms. Okay, let's just make it more neater. Let's remove this, and then you can just write the resistance there. So this gives us a resistance of 21,33 ohms. We already have the resistance of 6,67, so we'll just also need the resistance of L1. So the resistance of L1, so we can also use the same thing. R is equals to V over I. Our voltage is 20, and then our I will be 1,8. So then we have 20 divided by 1,8, which gives us 11,11 ohms. So we can also remove this. And we have 11,11 ohms. And we just know that we have a current of 1,8 amperes. Okay, so then let's start with this one. 6,67 R1 and L1, we know that they're in series. And remember, when we add the two, when we combine two resistors in series, it's just R1 plus R2. So in that case, it will be, so for resistance in series, it will be 6,67 plus 11,11. So it will be 11,11 plus 6,67. which will give us a total value of a combined value of 17,78 ohms. So then after getting that, what do we need to do? We already said that it's in series. These two are in series with each other, but they're in parallel with L2. So if they're in parallel with L2, we can use the formula 1 over Rp is equals to 1 over R1, 1 over R2. Or because it's two of them, we can just use this formula as well. So we know R parallel is equals to R1 multiplied by R2 over R1 plus R2. So this will give us R1, which is, we can take it as 17,78 multiplied by L21, which is 21,33 over 17,78 plus 21,33. Okay, I think I'm getting value of R parallel as 9,69. So that will be the total found in for R parallel, 9,69. So that means the total resistance of all this section is what? Is 9,69 ohms. So that means, as I said, this section is in series with that one. So that means the total now resistance of the circuit, our total will be equal to the parallel part and the series part, which is 9,69 plus 4, which will give us 13,69. So then now I can substitute. Okay, this is equals to 3,3 13,69 plus 0,6, and then the EMF is equals to, okay, is equals to 47.18 volts. So we my total EMF. So that is 47.18. So I'll just write it here, 47.18 volts. Okay. Then the next question says, bulb L1 burns out after a while. Assume that the resistance of bulb L2 remains constant. So bulb L1 burns out after a while, but we assume that the resistance of bulb 2 remains the same. So the question is, will bulb 2 continue to glow after bulb 1 burns out? Choose from yes or no, and support your answer with suitable calculations. Okay, now let's continue. 8.3. Bulb L1 burns after a while. Assume that the resistance of bulb 2 remains constant. Will bulb L2 continue to glow after the bulb? Choose from yes or no, support your answer with the suitable. So they're asking us if bulb 2 will continue to glow after bulb 1 burns out. So let's see. And they say that assuming that the resistance stays the same. So the resistance is 21,33. So let's see. If the resistance is 21,33, let's use the formula for EMF and see if there will still be any current in it flowing. EMF is equals to I R plus internal resistance. So we calculated as what? 47,18. And then looking for I, and then we have R, which is 21,33. Now it's remember, so now this part is gone, this whole part is gone. So we are left with L2. So that means L2 and R2 are now in series. So plus 4 and then plus the internal resistance, which is 0.6. That means it will be 47.1 divided by 21.33 plus 4 plus 0, so I is gonna be, can't put that in a calculator, it's gonna be 1, no, not 8, 1.82 amperes. So we can see that there is still current left in circuit, and you can also see that because this will now be the total current, a 1.82, this will be the current now flowing through L2, which is also higher than the previous current we had at L2. So yes, it will continue to flow.